This example problem is a continuation of an example problem from Module 9, where in Module 9 we did the flexural design, and in this module we're going to look at the shear design. What we're going to do is we'll determine the amount of shear reinforcement that we need using the ACI 31819 simplified shear procedure and the ACI 31819 detailed shear procedure. From our flexure design, we found that we needed this double T section, the 10DT26. I give us our section properties, and I also give us some information that we had from our flexure design. So during the flexure design, we determined our strength of the precast concrete, the pre-stressing area required, 8 half-inch strands, the depth of that steel, the effective pre-stress, so the stress in the pre-stressing after all of our elastic shortening losses, and then I also give us some information on our span length, our bearing details, and our live load and superimposed dead load. We need to take our pressure loads and turn them into distributed loads, and to do that we'll take the 15 pounds per square foot times the 10-foot width, which is the top flange width of our double T section, to get a distributed load here of 0.15 kips per foot, and that's for our superimposed dead load. We can then add that to the self weight of our beam to get the total dead load on the beam. For our live load, we just again take our 50 pounds per square foot times 10 feet to get our distributed load, and we can add that live load to our total dead load to get our service load, and then we can factor our dead load and our live load to get our total factored load, our ultimate distributed load here, 1.841. So now we're ready to turn to our shear design, and I give us here some general design requirements. In general, we need to make sure that phi Vn is greater than or equal to Vu. Our Vn is going to be a combination of our concrete shear strength and our steel shear strength. And our resistance factor for shear in ACI 318 is going to be 0.75. There's an upper limit as well that we need to make sure we're under. We need to make sure that our Vu is less than phi Vc times or plus 8 times the square root of F prime C BWD. And this upper limit just makes sure that we don't have crushing of the concrete that controls the failure. Finally, we have to determine what D we should use. ACI 318 allows us to use D as the max of our actual D and 0.8 H. So our actual D is 20 inches and 0.8 H is 20.8. So we'll use D equal to 20.8 everywhere other than the Vu times dP divided by Mu term. And I'll highlight where we should use the actual D on the next couple slides. Our critical section in ACI 31819 for pre-stressed members is going to be a distance h over 2 from the face of the support. So here we're told we have a 4-inch bearing, and our h over 2 would start from the edge of that bearing and go out a distance h over 2. So the distance that we'll use when calculating our moment is we assume that the center of our support is the center of our bearing, and that'll be the point of zero moment at the end of our simply supported member. So we need to go a distance length of the bearing over 2 to get to the edge of the bearing, and then we add that 0.5 H to the LB over 2 to get our X critical, or the distance from the center of our support to our critical section. So here we can see that'll be 15 inches or 1.25 feet. So this is the furthest, or this is the closest to the support where we need to check shear. It's not always going to be the most critical point in our shear design, but it will be the closest that we need to check shear to the support. So we can find our demand at the critical section just using some of our mechanics equations here. So our shear at the critical section we can find to be 40.1 kips, and our moment at the critical section we can find to be 51.5 kip feet. We now have all the values that we need to calculate our VC using the ACI 318 simplified procedure. This procedure allows you to, or requires you to calculate 3 different values from our table as shown here, and then the controlling value, or the minimum of those values, is going to be our VC. So we'll start with our V sub CA, and this will be 0.6 times 1.0 for our lambda. So normal weight concrete will have a lambda of 1.0 times the square root of 5,000 psi, so we use psi for ACI, plus 700 times 40.1 kips times 20 inches divided by 618 kip inches. And note, I'm highlighting here, but this DP, we're going to use the actual DP of our strands right there in that equation. Everywhere else we'll use the maximum of DP in 0.8H. So I'm going to close my bracket, and then we have 9.5 inches, which is the average web width for both webs in our double T section, times 20.8H, which is, 20.8 inches, which is 0.8H. And then I'm going to divide by 1,000 pounds per kip. And we'll get 187.7 kips. We can plug in our numbers into our V sub CB equation, and we'll get 0.6 times 1.0 times the square root of 5,000 psi, plus 700, and then times 9.5 times 20.8 inches divided by 1,000 pounds per kip. And this will give us a value here of 146.7 kips. So we can plug in our values into our C equation, I give that to you already, and find a value here of 69.9 kips. We need to take the minimum of these 3 values, so 187.7, 146.7, and 69.9. We can see the 69.9 is our minimum, so that'll be our controlling value. And we need to check to make sure that that value is greater than or equal to the equation here, or the value here, 2 times the square root of f prime c bwd, or 27.9. So it is, so our minimum value and our VC is going to be 69.9 kips. Because we're close to the end of the member, we also need to check to make sure, or check to see if we're inside the transfer length of our strand. So ACI says for shear, we're going to calculate our transfer length as 50 times our strand diameter. So 50 times 0.5 inches, we're using 1/2 inch diameter strands, which will give us 25 inches. And then our available transfer length is going to be the distance from the critical section, or the section where we're calculating shear, to the end of the beam. So this is going to be equal to our X critical, which takes us to the center of our support, plus the distance between the center of the support and the end of the beam, which in our case is going to be LB over 2. Note that this distance might be a little longer if you have some of the beam hanging past the bearing, past the support bearing. So here we're going to have our 15 inches critical section plus LB over 2, which is 2 inches, so 17 inches. We can compare our available transfer length, 17 inches, to our required transfer length, 25 inches. See that we don't have enough length to transfer the stress from the strand to the concrete. So our strand stress is going to be less than the effective stress. So we need to do 17 divided by 25 times that of F sub SE 178.4, our strand stress after all pre-stress losses, which will give us a strand stress here 121.3. So because we're inside the transfer length, this is the stress that we'll need to use in our pre-stressing strands. And we need to use this stress when checking to see if we can even use our simplified procedure. So our 121.3, we need to check because we have a fully pre-stressed member, we need to check that value versus 0.4 times F sub PU, which is 108 KSI. We see we're okay, so we can use our simplified procedure. But because we're inside the transfer length, now we have an additional upper limit, which we'll calculate on the next slide, of V sub CW reduced R. Our upper limit for our VC, when V sub C, when we're inside the transfer length, is going to be our V sub CW using that reduced force in the tendon. So we can calculate the reduced force in the tendon by taking our reduced stress from the previous slide times our total pre-stress area, gives us our force here of 148.5 kips. And then we need to calculate our V sub CW. To calculate our V sub CW, we need to find the compressive stress at the centroid of the section. And we'll use this equation here. We have a pre-top section, so our composite centroid is equal to the non-composite centroid. We don't have a differentiation between the two, so we'll lose these two components there. So we'll just have our compressive stress at the centroid equal our axial stresses. So our pre-stressing force, 148.5 divided by 689 square inches. So we'll get a stress at the centroid here of 0.216 KSI. We then can plug all these values into our VCW equation, which I do here, and we'll calculate and find our V sub CW equal to 61.7. And again, this is accounting for that reduced stress in the pre-stressing because we're inside the transfer length. We can compare this to the V sub C that we found using our simplified equations and see that this upper limit will control. So that's going to be our V sub C. So we can take that V sub C times 0.75 to get phi V sub C, which will be 46.3. And we can compare this to our V sub U, which is 40.1, to see if we need shear reinforcement for strength. So because our phi V sub C is greater than V sub U, we don't need shear reinforcement for shear strength, but because this phi VC is less than 2 times V sub U, we do require shear reinforcement, or we do require the minimum shear reinforcement. So we'll need to find the minimum shear reinforcement and provide that in our beam. We found on the previous slide that we don't need shear reinforcement for strength, but we do need to provide minimum shear reinforcement. So we'll need to calculate how much minimum shear reinforcement we need. So we can plug in our values into the given equations from ACI 318. We'll start at the top here, 0.75 times the square root of 5,000 PSI times our BW, which is 9.5 inches, divided by 60,000 PSI. We need to make sure our units are consistent here, so use PSI everywhere when you're using ACI 318. And then we're going to calculate the required shear reinforcement per foot. So I'm going to assume a spacing here of 12 inches per 1 foot. So we'll get a value here of 0.101 inches squared per foot. We can do the same thing for the two other equations from our minimum shear reinforcement table. And for equation D, we'll get a value here of 0.095 inches squared per foot. And for our equation from E, we'll get a value of 0.059 inches squared per foot. So the minimum shear reinforcement then is the maximum of our C and D. So the maximum of 0.101 square inches per foot and 0.095. So the maximum of those two is going to be 0.101 square inches per foot. And then it'll be the minimum of that max and 0.059 square inches per foot. So 0.059 is less than 0.101, so that'll be the controlling minimum shear reinforcement. So that'll be our required shear reinforcement per foot in our beam. We'll also need to check the maximum spacing requirements. So I provide them to you here in this table, and we'll continue this on the next slide. When we're calculating the maximum spacing requirement, we need to check the required V sub s and see if we're less than or greater than this limiting factor 4 times lambda times the square root of f prime c times bwd. So we can calculate that value, which I do here, and find that the limiting value is 55.9 kips, and then we need to calculate the required V sub s. And to do this, we'll take our V sub u divided by phi, so 40.1 kips divided by our phi, 0.75, minus V sub c, which is 61.7 at the critical section where we're checking. We can see we have a negative value here. So this is obviously less than that 55.9. So we can use these values for our maximum spacing. So our maximum spacing is the minimum of 3/4 h. So 3 times 26 divided by 4, 19.5, and 24 inches. So 19.5 is less than 24, so we'll use 19.5. So now we know the minimum amount of shear reinforcement per foot, and we know the maximum spacing. So now we can try different combinations of stirrups, or we can use welded wire mesh as well. So here we're just going to try using number 3 bars spaced at 18 inches on center, and we're going to assume that we have one number 3 bar in each one of the webs of our double T. So we'll have 2 number 3 bars, so 2 times 0.11 square inches divided by 18 inches, and then we're trying to find the total area of shear reinforcement provided by foot. So we take that times 12 inches divided by 1 foot, and we can see we have a value here of 0.147 square inches per foot provided. This is greater than our required value, and our 18 inches is less than our maximum spacing of 19.5 inches. So this shear reinforcement will satisfy our design requirements. The last thing that we need to do for the simplified procedure is we need to calculate the actual phi Vn and make sure that it's greater than or equal to V sub u. And to do this, we'll need to calculate our V sub s that's provided by the reinforcement that we have. So we had 2 number 11 bars times 60 ksi times our D, which is 20.8 inches, all divided by our spacing, 18 inches, and we'll get a V sub s here of 15.3 kips. We can add that value to our V sub c, which we found, to get a V sub n of 77 kips, and then take that times 0.75, our phi factor, to get our phi sub Vn of 57.8 kips. Check this against our V sub u, 40.1. We see where our phi Vn is greater than Vu, so our design's okay. We need to check the actual capacity along the length. Even though we just did one sample calculation of the critical section, you can see here I provide the rest of the checks along the length. And we need to make sure that our phi Vn is greater than our Vu, which you can see here it is along the entire length. And here we're only checking L over 2. We'll have a symmetrical shear diagram and resistance diagram on the other side. So here our design for shear is okay. The next part of the problem is to repeat what we did on the previous slides, but using the ACI 318 detailed procedure instead of the simplified procedure. To do this, we need to calculate a few other shear demands and moments than we had before. So we also need to calculate our dead load shear, our factored shear from externally applied loads, our dead load moment, and our maximum factored moment from externally applied loads. So you can see those values here, and I calculate them for us, and we'll use these values in our flexure shear capacity, our V sub CI, and web shear capacity, V sub CW equations. For our flexure shear capacity equation, we need to calculate our cracking moment at the critical section. And to do that, we'll need several other properties. So I give some of them to you here. We have our section modulus, which is the non-composite and composite section moduluses are equal because we have a pre-top section. We also need our strand stress. So we're going to reduce our strand stress the same way that we did earlier in this example. So we'll get the same reduced strand stress, the same reduced force in the pre-stressing strands. And we'll also need the strand eccentricity at the critical section, which we can find as shown here. So we can then plug all these values into our cracking moment at the critical section. So we'll have our section modulus, so 1,514 inches to the third, times 6, times 1.0 for normal weight concrete, times 5,000 PSI. I'm going to convert this to kips right here, plus 148.5 kips divided by our gross area, 689 square inches, plus 148.5 times our eccentricity, 14.3, divided by our non-composite section modulus, 1,514 inches to the third. And then, minus 292 kip inches divided by 1,514 inches to the third. So we'll get this value then to be 2,799 kip inches. So this is our M sub CRE. We can finally plug all of the values from the last two slides into our V sub CI and V sub CW equations. So that's what I'm showing you here. So we plug all of our values into our V sub CI equation to get a total V sub CI of 208.7 kips. We can compare this to the lower limit, 2 times square root of F prime C BWD, 27.9. See that we're greater, so we can go ahead and use that V sub CI. And then we can do the same thing that we did earlier, calculating our V sub CW. So I'm going to just go through this quick, and we can find a V sub CW equal to 61.7 kips, which is the same as we found before. Our V sub C is then equal to the minimum of V sub CI and V sub CW. So the minimum of 208.7 and 61.7, so 61.7 kips. And we can take that times our phi 0.75 to get our phi VC equal to 46.3. We can see that because V sub CW controls, and because it also controlled at the critical section in our simplified procedure, it's going to be we have the same phi VC using both the simplified and detailed procedure at the critical section. This won't always be the case, but it is in this example. And because it is, we don't need to go back through and recalculate anything with our shear reinforcement. All of that will be the same. So we'll use the same shear reinforcement that we found from the simplified procedure. So next I wanted to show you a few plots comparing different values of our shear along the length. And the first one here is our V sub CI compared to our V sub CW along the length. So you can see when we're close to the support, our V sub CW is going to control. So that'll be our minimum. And then as we get out into our span, that's where our flexure shear is going to control. So you can see then our V sub CI is going to control. And this will typically be the case for our pre-stressed concrete beams. Our next plot here is our concrete shear demand versus capacity using the detailed procedure. And you can see along the whole length here, outside of our critical section, our phi VC is greater than VU, it's always greater than VU, but about there we can start, or we don't need minimum shear reinforcement anymore. So whenever our phi VC is greater than 2 times VU, we don't need minimum shear reinforcement anymore. Although it's good practice to provide it, just to make sure that we have a ductile response. The last plot here is a comparison between the simplified and detailed approach. So you can see the gray here is the detailed and the blue is the simplified. And you can see with the detailed procedure, we get a little more capacity right in this range. And it's actually the difference between our phi VC being less than or greater than our VU, kind of right in this range here. So anyway, typically if you use the detailed procedure, you'll get a slightly higher capacity than you do if you use the simplified procedure. And that concludes this example.